let's go to start to discuss this problem. In this problem, we have a function f of xy 3x minus 4xy plus 9y. We have a point and we have a direction. We want to find the directional derivative of the function at the point P1, 2, following the vector v equal 3/5 I plus 5j. So in some way we want to find how much it will change the function when we move in this direction. And the change in the function, the directional change in the directional v of the function is obtained by finding the gradient and finding the projection of the gradient onto the v direction. So let's go to apply this equation to this problem, and later on let's go to justify this equation. Okay, so we have a lot of computation to do, so the first things that we have to find is the gradient of f. The gradient of f is a vector field, and the gradient of f is obtained by obtaining the partial derivative of x in the I direction plus the partial derivative of f respect to the y direction. So it's a vector field, and in this case the partial derivative of f respect to the x is 3 here, is 4y here, so it's 3x minus 4y in the I direction, plus the partial derivative of f respect to the y is 4x minus 4x plus 9 in the j direction. And this is the gradient of f. The gradient of f is pointing in the direction of maximum increase, but we are going to move in this direction, so it's not have to be the same thing. So if we are at the point 1, 2, the gradient of f will have the value 3 by 1 minus 4 by 2 in the I direction plus minus 4 multiplied by 1 plus 9 in the j direction. So the gradient of f at the point 1, 2 is the gradient is 3 minus 8 is minus 5. Minus 5i plus, 9 minus 4 is also 5j positive. So the gradient of f is minus 5i plus 5j. What is the derivative of v? Well, the derivative, the directional derivative of f in the v direction is the gradient of f dot the unitary vector v. So we have to check that this v is unitary. And this v, the magnitude of v, b, is the vector of 3/5 I plus 4/5 j. And indeed, the magnitude of this vector is square root of 3/5 squared plus 4/5 squared equal 3 squared is 9 plus 4 squared 16, 16 plus 9, 25, 25 divided by 5 is 1. So we are correct. So let's go to do it. So the variation of the function in the v direction, the variation of the function in the v direction is the projection of the gradient on this direction. The gradient is the vector minus 5i plus 5j. And the v vector is the vector 3/5 plus 4/5 j. And the dot product is minus 3 5 minus 3 plus 4, which is 1. And what it means 1? It means that if you are stopping at the point that we are considering, the point 1, 2, and you see the function, this is the point, let's say 1, 2, and you see the function, and you make a step, an infinitesimal step in the direction of the vector v, let's say this is the direction of the vector v, the change in the function, the instantaneous change in the function, the slope is 1. And the slope is being measured on the tangent plane to the point. The tangent plane is the plane that keys the surface at the point 1, 2, I think it was 1, 2, 1, 2. It keys the surface in one point, the point 1, 2. We will see this later. So now, let's go to be able to explain and justify this equation. The partial derivative in the v direction of the function f equals the gradient of f dot the direction, unitary direction. So this is unitary direction. How we can justify this? Okay, the way to justify is the following one. When we make a change in the function because we move in the x direction and in the y direction from a point, let's say 1, 2, the change in the function is the partial derivative of f respect to the x by d dx plus the partial derivative of f respect to the y by d dy. And this change in the function takes place in the tangent plane to the surface. So this can be written like this. The change in the partial derivative of f respect to the xi plus the partial derivative of f respect to the yj dot product d dxi plus d dyj. And d dxy multiplied by d dyj is the change in position, ddr. And what is that in parentheses is the gradient of f. So the gradient of f, ddr, is the change in the function. Perfect. So we know now that the gradient of f, we have discovered that the definition of the gradient of f makes sense. Is the partial derivative of f respect to the xi plus the partial derivative of f respect to the yj. And now we want to justify the equation of the partial derivative in the v direction of the function f. So let's go to do it like this. Let's go to write ddf like the gradient of f scalar ddr. But ddr will have a direction and will have a magnitude. The vector ddr will have the magnitude ddr and will exist on the direction v. So the change in f divided by the change in r is the gradient of f dot v unitary. And this is what we call the change in the function v in the v direction. I hope now it's clear. Now one more word about how is this related to the physics. Normally in physics, the function f of xy is being thought as a potential function of xy. So we imagine that the function f of xy represents energy that exists at the point xy. If you move from another point, the function, the energy will change. So this procedure will allow us to calculate what will be the change in the potential energy when we move in some direction. And the change in the potential energy will be the gradient of E sub P dot the direction, unitary direction. Okay, let's go to solve the next problem. Now let's go to solve problem 2. In this problem, we have a new function, f of xy e to the x sine of x, sine of y, and the point P is the point 1, comma, pi divided by 2. And the problem is asking what is the variation of the function in the direction minus I. What is the variation of the function f of xy when you move in the minus I direction? So the vector v is the vector minus I. And this will be the gradient of f dot v. So the directional derivative of the function in the I direction, in the minus I direction of f of xy, will be the gradient of f dot minus I. And what will be this? Now we need to calculate the gradient of f. The gradient of f is the partial derivative of f respect to the xi plus the partial derivative of f respect to yj. The partial derivative of x respect to the x is e to the x sine of y. I plus the partial derivative of x of f respect to the y is e to the I cosine of y. And this we need to calculate this at the point x equal 1, comma pi divided by 2. So the gradient of f will be e raised to the power 1 sine of pi divided by 2, which is 1, in the I direction, plus e to the power 1 cosine of pi divided by 2 in the j direction. So this will be ei. And what will be the directional derivative of the function in the minus I direction is the projection of the gradients in the direction v, in the direction minus I. So it will be ei, which is the gradient, dot product minus I. It will be I, scalar I is 1 minus e. So what it means this? It means that if you move in the minus I direction, the instantaneous change of the function will be minus e. Okay, let's go to the next problem. Now let's go to this problem to explain how to solve it. So it's exactly the same thing. We have a function. We need to find the gradient of the function. So we need to find the directional derivative on the v direction, but we need to find the unitary v direction of the function f of xy c. Now it's a function of 3 variables, and this will be exactly the same. It will be the gradient of f dot the unitary vector v. So the first observation that we can do here is that this v equal minus 1i minus 1j plus 1k is not a unitary vector because the magnitude of v is a square root of 1 squared plus 1 squared plus 1 squared, which is a square root of 3. To convert this v into a v hat be unitary, we need to take the vector and divide by its magnitude. So it will be the vector minus 1 square root of 3i minus 1 over square root of 3j plus 1 divided by square root of 3k. That is the directional vector that we want to use, we need to use in this problem to find the derivative, the directional derivative of the function. So let's go to do it, but it's exactly the same. So the function f of xy is x squared plus y squared plus c squared. So f of xyz is x squared plus y squared plus c squared. You might wonder, what is the gradient of f? The gradient of f is 2xi plus 2yj, the partial of f respect to y, and the partial of f respect to c. Okay. So, what is the directional derivative in the v direction with the hat of the function f of xyz? Is the projection of the vector onto the direction 2xi plus 2yj plus 2ck dot projection on the directional vector, which is minus 1 the square root of 3i minus 1 square root of 3j plus 1 square root of 3k. So this will be equal to x minus square root of 3 minus 2y square root of 3 plus 2z square root of 3. And we need to evaluate this at the point xyz, which is the point 1, 1, 1. So the directional derivative of the function on the unitary direction of f will be minus 2 square root of 3, because x is 1, minus 2 square root of 3 plus 2 square root of 3. So the total will be minus 2 square root of 3. What it means, minus 2 square root of 3? It means that when you move in this direction, the function will decrease. Now, how is related this with the physics? In physics, we have potential function, x, y, and z in the space. And the potential function, normally the function that we will talk, it comes from a force that are central forces. But the usual potential for interaction, for central interaction, are of this type. 1 divided by square root of x squared plus y squared plus c squared. If we want to put it, the function nicer, we can make it like this. We can put a k here, q1 and q2. So it will say the potential energy that two charges q1 and q2 have. Or maybe we can relate it to potential gravitational energy. This is for potential electrical energy. Now, if we want to express the potential gravitational energy at any point x, y, z, the expression for the potential gravitational energy is G, that is a constant, m1, m2, divided by the square root of x squared plus y squared plus c squared. And how is related the potential energy in physics with what? With the force. The force is minus the gradient of E sub P. We will use this equation to do problems. The force that exists on the particle of mass m can be calculated given the potential energy as the minus gradient. So is the vector field. The force is a vector field that is going in the opposite direction as the gradient. Okay, let's go. Now let's go to solve this problem. It's a find the gradient of the function 3x plus 5y squared plus 1 at the point 2, 1. To find the gradients means to find a new vector field. And the vector field will point in the direction of maximum increase of the function f of xy. So we pass from division x, y, f of xy, from division of the value of the function at the point xy to division in xy of a vector field that is on the plane xy. So let's go to find the gradient. The gradient of f is a vector field, is the partial derivative of f with respect to the x plus the partial derivative of f with respect to the yj. What will be? Will be 3I plus the derivative of f with respect to the y, 10y j. So this is the gradient of f. So at every point now, in the plane xy, there is a vector field. For example, at the point 1, 1, 1, what is the gradient? The gradient is 3i, 1, 2, and 3i, and 10y, 1, 2, 3, 4, 5, 6, 7, 9, 10. So the vector is this one. This is the vector that is the gradient of f. So I have a vector field at every point. At every point, I have a vector. And what will be the gradient of f when I move in the x direction on here? It doesn't depend the gradient, so it will be the same vector. Parallel. If I put here, at this point, it will be the same vector, parallel, because the vector field, the gradients, doesn't depend on x, so it will not move. So the idea that constructing a vector field from an scalar function is quite powerful. And why is powerful? Why in physics is powerful? Normally, in physics, you can have a potential electrical energy same like this one. E sub p of xy, 3x plus 5y squared plus 1. And you may wonder, what is the vector field of force? In what direction is the force acting on a body at every point? And the force acting on a body in every point is in the negative direction of the gradient of E sub p. And what is this direction? Is the direction minus 3i minus 10 times yj. So starting from an electrical potential energy like this one that depends on x and y, you find a vector field that say what is the vector field at any point in the plane xy. For example, at x equal 1, comma 0 is minus 3. The vector field will point it in this direction, minus 3. And what if I put, I am here on x equals 0 at the point 1, 0, comma 1? Well, the vector field will pointing in that direction minus 3i, minus 3i, minus 10 by 1. So the vector will be like this, minus 10. The sum will be this vector. So the force will go in this direction at this point. Let's go to the next problem. Well, to find the gradient of f of xy, f of xy equal natural log of x squared minus y at the point 2, 3, we'll do the same thing. It has no point to do it. It's very easy. Okay, let's go to the next problem. Okay, let's go to do this problem. It has no trick. The problem has no trick. But let's go to change the problem. Let's say that we have the potential energy, E sub p, of x, y, z equal 3x squared minus 5y squared plus 2c squared. And we want to find what is the vector force at the point 1, 1, minus 2. So how we will do? The force, the field, the gradient of E sub p is related with the force in a way that the force is pointing in the negative direction of the gradient. So how we will find the vector field that is related with this potential energy? So we have energy at the point 1, 1, which is 3 minus 5 plus 2. 3 minus 5 minus 2 plus 2, 0. So at the point 1, 1, there is no potential energy. What is the potential energy at the point 1, 1 minus 2? Is 3 by 1 minus 5 by 1, which is minus 2, plus minus 2, plus 2 squared is 4, 4 by 2 is 8, and the sum is 6. 6 units of energy at the point 1, 1 minus 2. So the energy is changing in space, x, y, z is changing. And we want to know at every point what is the force. The force, that the vector field that exists in space, is minus the gradient of A sub p. So let's go to do the gradient. So the gradient of A sub p is a vector. And the vector, in some books, write it like this, the gradient of E sub p. And they put a vector here to denote that is a vector field. So we know how to find the gradient. The gradient is the derivative of A sub p respect to the x. The gradient of E sub p is the derivative of E sub p respect to the xi plus the partial derivative of E sub p respect to the yj plus the partial derivative of E sub p respect to the ck. What is the partial derivative respect to the x? So the gradient of E sub p is the partial derivative is 6x I plus the partial derivative of respect minus 10i minus 10i j plus 4ck. And at the point 1, 1 minus 2, 1, 1 minus 2, it has a value. What is the value? The gradient of E sub p, the vector, evaluates at the point 1, 1 minus 2 will be 6 by 1 I plus 10 by 1 j plus minus 8, 4 by 2, 8 minus 2 k. So the gradient will be 6i plus 10j minus 8k. And what will be the force at the point 1, 1 minus 2? The force that exists at the point 1, 1 minus 2 is the force minus 6i minus 10j plus 8k. This is the force that will act on the particle of mass m and will accelerate the particle. Okay. There is a small mistake that I did that is here when I did the partial derivative of E sub p or the function f respect to the y is minus 10y and I wrote plus 10y. So this is a minus sign, this is a minus sign. Sorry, it will not alter in any case the ideas that I'm writing. So the correct answer would be this with a minus sign, this with a minus sign, and this with a plus sign. This component. I'm sorry. Now let's go to solve problem 7. Now let's go to solve the next problem. Let's say find the maximum value of the directional derivative of the function at the point 1.0. So find the derivative, the partial derivative of the function f of xy in an unknown direction, v, unknown direction, in such a way that the function will change the maximum value. If you remember, the directional derivative is obtained by the gradient of f dot the directional vector. So the question is the v directional unitary. So the question is, when you will obtain the maximum value of the directional derivative? Well, when the vector, unitary vector, this 1v, will be parallel to the gradient, because this is the gradient of f, the magnitude of the gradient of f, by the magnitude of the gradient of v, which is 1, by the cosine of the angle. So if the angle between v and the gradient, between the direction and the gradient of v is 0, you will have the maximum increase. So as a solution, the maximum value of the directional derivative is the magnitude of the gradient of v. Oh, so let's go to find the gradient of f, What is the gradient of f? The gradient of f is 2xi plus, is 2x is 2x plus 2y ji plus 2x in the j direction, the partial derivative of the function in the y, in respect to y. The gradient of f at the point 1, 0 is 2i plus 0 plus 2j plus 0j, plus 2j, here is 0. The magnitude of the gradient of f is a square root of 2 squared plus 2 squared, which is a square root of 8. So the maximum change in the function in the direction 1, 0 is a square root of 8. And of course, a square root of 8 can be written like a square root of 4 by 2, and a square root of 4 is 2, a square root of 2. So this is the maximum change in the function. It occurs in the direction of the vector. And what is this direction? Oh, you can find the direction. The direction is at the point 1, 0, the direction is 2. The direction is here, is 2i plus 2j. And what is the direction? The direction is 2. The v direction, unitary, is 2 divided by a square root of 8i plus 2 square root of 8j. This is the direction in which you have to move to obtain the maximum change in the function. Now let's go to do this problem. Find the maximum value of the directional derivative of the function f of x, y, z equal x, y squared, c squared. So at every point in Spain, I have a value. At the point 2, 1, 1, 2, 1, 1, I have a value. What is the value? The value is 2 multiplied by 1 squared, multiplied by 1 squared, so the value is 2. So the value of the function is 2. So is 2, 1, 1 the 8th, and the value, we put a flag, and the value is 2. If you go to another point, the value will be different because x and y and z will be different. Can I represent f of x, y, z? No, I cannot represent unless I put flags. For example, the flags at the point 3, 0, 0 will be 3 by 0 by 0 will be 0. So at this point, the flag will say a 0. At this point, all the flags will say 0 because the y is 0. At any point in the plane x, y, the flags, for example, at the point let's say 2, 0, the flag will say 0. So at the plane xy, the value of the function is 0. So the value of the function cannot be represented graphically speaking. It says that when you move from one point to another point, when you move from the point 2, 1, 1, at the point 2, 1, 1, the value we set that is 2 by 1 by 1 is 2. At the point 2, 1, 1, this point, the value of the function is 2. So when you move, the function will change. So the problem is asking you in what direction you have to move to obtain the maximum increase in the value of the function. If you move in the x direction, if you move in the x direction, the x will change, but the c will remain the same. So it will be a change in the function. But in what direction you have to move? So the answer is you have to move in the direction, v direction, of the gradient, of the gradient of f dot u of v. If you move in the direction of the gradient, you obtain the maximum increase in the function. And what is this direction? Well, the gradient of f will be the derivative respect to the x of f, I, plus the derivative of f respect to y, partial derivative of f respect to y, partial derivative of f respect to z, k. And the gradient will be, because f of x, y, z is, f of x, y, z given is x, y squared, z squared, the gradient of f will be the partial derivative of x, y squared, z squared I. The partial derivative of f respect to the y, 2x, y, z squared, j, plus the partial derivative of f respect to the z, 2x, y, z, k. And the gradient of f evaluate at the point 2, 1, 1, 2, 1, 1, it will be 2 squared 4. 1 squared plus 1 squared I plus 2 times 2 by 1 squared k plus 2 times 2 by 1 k. So the gradient of f, the vector gradient of f, will be 1i plus 4j plus 4k. So if you move in this direction, in what direction? In the unitary direction, u, with the direction v, is the gradient of f divided by the magnitude of the gradient of f. And what is this direction? 1 divided by a square root of 1 plus 16 plus 16 I plus 4 divided by a square root of 16 by 16, 32, 33 j plus 4 divided by a square root of 33k. If you move in this direction, this is the direction of maximum increase in the function. The value of the change of the directional derivative of f is the gradient of f dot this direction v. But this is a unitary direction. The magnitude unitary, so the dot product will be the magnitude of the gradient of f by the magnitude 1 by the cosine of the angle, but the angle is the same, is 0, because I'm moving in the same direction as the gradient. So the directional derivative of the function will be exactly the magnitude of the gradient of the function at the point 1, 1, 2. And what is the magnitude of the gradient of the function at the point 1, 1, 2? Well, the gradient of the function is 1 plus 4 j plus 4k, and the magnitude of the gradient is square root of 33. So the final answer is square root of 33. Now we are going to develop another concept, and it's the concept that gradients are perpendicular to level curves. And why is that? Well, it's here. ddf is the gradient of f scalar ddr. So if you are moving in the perpendicular direction of the gradient of f, the change in the function will be 0. So the gradient of f is perpendicular to level curves. So in this problem, it say find the normal vector. So find the gradients to the level curve. What is this level curve? So the level curve f equals 6 is when 6 minus 2x minus 3y is 6, or when 2x equal, when minus 2x equal 3y, or when y equal minus 2/3 of x. So the level curves, x and y, the rectilinear line with a slope minus 2/3. So let me paint the graph, the function here. So the rectilinear line with a slope minus 2/3 is this line, and over this line, the value of the function is 6. And what happened with the value of the function is 6? What is the perpendicular vector? The perpendicular vector is the gradient. So let's go to find the gradient of f. If we find the gradient of f, we'll find the normal vector to the level curve. So this is the level curve. And this is the gradient. So let's go to find it. The gradient of f will be minus 2 I minus 3j. So the vector minus 2i minus 3j is the vector that is perpendicular to the level curve. Wow. One thing more, when we have a function that is not f of xy, let's say f of xyz, let's say x squared plus y squared plus c squared, how we will find the normal vector? The idea is the same. Now there is level surface. Now in 3 dimensions, there is no level curve, there are level surface. And the gradient is perpendicular to the level surface. So how we will do? Let's say that f of xyz is equal to 6. So theta is the level surface. Theta of xy will be 6 minus x squared plus y squared. And the gradient of f at the point will be perpendicular to this level surface. This surface is the surface of a paraboloid that is doing like this, okay? It's doing like this. And the gradient is perpendicular to the level surface. So the gradient will do like this at every point. Let's go, well, we will calculate later the gradient at any point.